Okay, this is video 1 for the force unit notes. In this learning goal, or with these learning goals, I want you to understand what equilibrium is. I want you to be able to solve problems involving gravity, describe what a field is used for, and solve problems involving elastic forces. All right, so let's go ahead and get started. Now, before we can start talking about static equilibrium, we need to be able to make a free body diagram or a force diagram. That is an essential skill that you have to have in order to judge whether something is in equilibrium. So let's start by making a force and free body diagram for an object flying through the air. So here's our object and it's flying through the air. Well, some force is acting on it. Well, we know that there's going to be gravity between the center of mass of the ball and the center of mass of the earth. And there's also going to be some air resistance. Notice I did not draw any forces propelling the ball. Just because something's moving does not mean that there has to be a force, causing it to move. So, with that said, that's our force diagram. For our free body diagram, we represent the ball as a dot, and we can go ahead and draw those forces on here. Now, notice that this force for the air, it's not on an axis. It's at some angle. What that means is we can represent that force from air as the sum of two perpendicular vectors. So this would be the x component of that air resistance, and this would be the y component of that air resistance. And the way we would calculate them, it's always hypotenuse, trig, angle. So since the x component here is adjacent to the angle, we would use the cosine function. And since the y component is opposite of that angle, we would use the sine function. So there you have it. All right, another classic example is an object sitting on a ramp. Okay, once again, we would have gravity. It's always vertically down. We would have a normal force, and since this is on an incline, the normal force would be located a little closer to the front of the box, and it would be perpendicular to the ramp. And then we would have some friction. I don't know if it's static or kinetic, it doesn't matter at this point, but there would be some friction that opposes sliding. So that's our force diagram. Now for the free body diagram. So there's our free body diagram. Once again, notice if the ramp is angled at some angle, we'll call it theta, theta would also be found right here. Also notice that since this gravitational force is not on an axis, we can represent it with two perpendicular vectors. When added together, it gives us that FG. So we would have an FG x and an FG y. And this time, to calculate FGX, hypotenuse, trig, angle, it would be FG times sine of theta, and FGY would equal FG cosine of theta. So notice that, what is opposite theta, what is adjacent to theta, that dictates whether you use sine or cosine. All right, our next example, let's say we have, um, a person hanging from a cable. Well, for this, we would have the person's gravity vector. We would have some tension, I'll call this Ft1, and we would have some tension Ft2. So when we go to make our free body diagram, it would look something like this. And notice that, once again, we have some angles. Oh, let's go with theta and gamma. So that means that we can resolve these into their x and y components. I'll leave it up to you to figure out the formulas for those. Now, just to kind of wrap this up, notice that in all of these cases, we had forces that were at an angle, which meant that we could resolve the forces into the perpendicular vectors that add together to make them. So, once again, as an example, if this is angled at, say, theta, and this is some vector f, we could put two vectors head to tail, and we can add those two vectors together to give us that original vector f. And that would be the formulas for those two right there. All right, so continuing on with this. We now know how to make our force diagrams. The next thing we have to worry about is what exactly is net force. And this is simply the sum of all forces acting on an object. And to be more specific, the vector sum. The way I like to write this is with the sigma symbol. So it'd be sigma F. Now, since we can study forces on single axes, we can identify the net force on just the x or just the y axis. So we can have like a sigma Fx or a sigma Fy. Okay, now this all leads us up to something called the Newton's first law. This is a lengthy definition. Okay, so this is something you could probably recite in your sleep. An object in motion stays in motion, an object at rest stays at rest. But there are some important things here. If it's moving, it wants to move in a straight line. Curved motion, circular motion, is unnatural. Objects would much, much rather stay in a straight line. And really, if you think about this, this all comes down to what we call equilibrium. In order for Newton's first law to work, the net force needs to be zero. Now, just because the net force is zero doesn't mean that an object has to be at rest. All that has to happen is that all the forces need to add together to give us zero. So an object in motion, if it's moving at a constant velocity in a straight line path, can be in equilibrium. So Newton's first law is all about equilibrium. All right. Inertia. So inertia is the tendency of an object to maintain its state of motion. So if it's moving, it wants to stay moving. If it's at rest, it wants to stay at rest. That's its state. And this really is Newton's first law. In fact, sometimes the first law is called the law of inertia. Mass. We really don't know what mass is or what causes mass. But what we do know is that mass is a measurement of inertia. The larger an object's mass, the more inertia it has. So, equilibrium. When the net force acting on an object is zero, the object is said to be in equilibrium. So, that happens when the vector sum of all forces on the x-axis equals zero, and when the vector sum of all net forces on the y-axis equals zero. And when you get to college and learn about 3 dimensions, we can have a z-axis as well. So let's go back to an example we had on the first page, the person hanging from a cable. So for the person hanging from a cable, all right, so that was our free body diagram. And remember, we were able to resolve this into the x and y components. So, in order for there to be equilibrium, the sum of forces on the y-axis, well, that would be your ft1y plus ft2y minus your gravity would have to equal 0. So what that would mean then is you would have ft1 sine of theta plus ft2 sine of, I call it gamma, minus mg would equal 0. So that would be one equation right there. And then on the x-axis, we would simply have ft1x minus ft2x equals 0. And notice how I'm following the Cartesian convention. Everything up and to the right is positive, everything left and down is negative. Now, looking at this, we can see that we have two unknowns. That's assuming you know the mass. We don't know ft1 and we don't know ft2, but at this point, we have two equations. So using a little bit of algebra, we could solve for both of those unknowns. All right, that concludes this video.